This question reads, a discrete time signal x of n, shown here, sketch and label the following signal, this one. So that is our question. It involves the unit step function and function of x, function of n, or a sequence of n that is delayed or that is advanced to it by 2 units. So we need to remember a few things, that a delayed unit step function defined by u of n minus k will always be equals to 1 when n is bigger than or equals to k and 0 otherwise. So this sequence normally takes the form if this is k and this is n, then it will start at of n minus k. So it will start at k value instead of starting at 0. So this will be at 0, 0, 1, 2, etc. So that is how we represent u of, or the unit step function that is starting at k. It is normally called, it is a delayed function. It starts at a delayed value of k. So having remembered that, then we also remember this function, which is a relationship between the unit step function and the impulse sequence delta of n. But you're not going to use this much. What we actually need to remember is that we can also have this, whereby an advanced unit step minus the unit step will give you a value between the range of minus k value is less than n, and where n is less than or equals to 0. So this is the other condition that we remember, and we can always figure that out. But for now, that is beyond the subject of the study. But the most important thing to remember is this, that an advanced unit step function having depicted by un of u of n plus k minus u of n will be equals to value. It will look something like this. Let's assume for once that k is equals to 1. So I've just drawn, this is how u of n plus 1 would look like. We normally say that this one is going to be equals to 1 for n is bigger than or equals to minus 1 and 0 otherwise. So remember, we are taking the negative value of this, or rather we can simply say this can also be written as minus 1 is less than equals to n. So that being said, we are saying that our function will have a value of 1 for any value from -1, 0 is to have a 1, all the way towards infinity. So it will have positive values. And also, we also know that the u of n will have a value of 1 in beyond 0, or anything bigger than 0. And therefore, when we take this one minus this one, we normally say that we are minusing, therefore we are minusing the ones that are in green. So when you minus, it is like you are removing. We are going to be removing all these ones on the right hand side, and we are going to be left with -1 as our result. So having said that clearly, I just probably forgot to remove this one as well. Sorry. I also need to remove the one that is represented by u of 0, which is that one. And therefore, we are only left with this 1 alone, because the ones that were starting from here, from 0 all the way towards infinite n, have been subtracted. Therefore, we are only left with that. So that is, I've just illustrated with this equation where k is equals to 1, and we are only left with this -1. And I think I should make a correction here that this doesn't have this symbol here should read, this symbol here should read less than only, less than 0, not less than or equals to. So we're saying that it will be less than equals to k, or the range will start with minus k, less than or equals to n, and n is less than 0 and not less than or equals to. Therefore, we are clearly only left with this term. So having given that illustration, now we can come back to our problem. And now our problem says that we have this term that is almost similar to the one that I have used to describe. And what we need to be concerned about is this section of the equation. And this section of the equation simply is in the form that we require. And for that reason, we just needed to make sure that we can express it as plus n plus k instead of having only n here. And the one that is on the right hand side should have no k. Therefore, what I do with that is I let n minus 2 that is here be equals to m. And when we say that is the case, then we are going to be having u of m, because we have said n minus 2 is equals to k, and n will be equals to n plus 2. And therefore, we are going to be having u of m plus 2 minus u of m. And therefore, it is now in the form that we require here. And therefore, once we have found that out to be the case, then we can definitely express it as such, which I have done here. And therefore, what we are going to have is that we are going to be left what is on the left hand of the curly bracket, and you are going to be saying this is going to be the case. Remember, when we were talking about u alone, we were saying 1, but now because we have x of m, we are going to be having x of m here, and therefore on the right hand side, we are going to be having minus k. Remember, our k now has become 2, and the range, again, I will make this correction here that we don't have less than or equals to, we only have less than. So this now becomes our new range, and we can express our equation only as this. Now, if we now substitute our m back to how it was before, we still have now our original equation, but now on the right hand side we have our equation that is in the form that is better than we had earlier. Therefore, we are going to be saying is equals to equal x of n minus 2, and now our range takes the original form, which was n minus 2. You place it back where it was by replacing this m. So what we do is that we solve the limits alone without touching anything else. And then when we solve the limits alone, we are going to be to end up with this as part of our equation. But now our limits, you simply add 2 on every side of the inequality. We have plus 2 becomes 0, plus 2 becomes n, and plus 2 becomes 2 here. And therefore, this becomes our new equation. And therefore, we can now be able to draw this diagram, this equation now from what we already know. And before we actually draw this, we just need to remember that from this figure that we had here, we know that when n, so our new limits, again, what we need to remember is this one, these two limits, between 0 to 2. Therefore, we need to determine what is the value of x of n at 0. And you can clearly see from this equation is equals to 0. X of 0 is 0, x of 1 is 1, and x of 2 is 2. That is within our limits that we have. So x of 1 is 1, and x of 2 is 2 here. That is what we are going to be using down here. And therefore, that is what I've simply done. But now we are not, I have just written this one above here. And therefore, what we actually now need to solve for is x of n minus 2, because that is our problem that is right here. So we ask ourselves what will be the value of x of n minus 2 when n is equals to 0. And we have seen that when n is 0, we have x of 0 is 0. Therefore, what will be x of n minus 2 will still be 0 because it is equivalent to this term here. And therefore, but now our n will change and be to say that we are getting this to be equal to this. So when you say 0 is equals to n minus 2, you actually figure out that your new value of n, if you do actually call it n prime, is equals to 2. And therefore, we are going to be saying that our x of n will be 0 at this, will be 0 at n prime, at our n prime, which is now representing x of n minus 1, or x of n minus 2, we will be having a 0. Similarly, we know that x of 1 is 1 at n is equals to 1. And therefore, when we equate this same here, we are going to be equating this term with this term at the center. And therefore, we say that n minus 2 is equals to 1. And we have our n is equals to 3. And therefore, that value is 1 here. We put a 1 there. And lastly, we equate this term with this term, and we know that the value here is 2. Therefore, we equate this value is 2 there. Therefore, our new value of n becomes 4, and therefore our equation takes the form of 0, 1, and 2 at values 2, 3, 4 respectively. And therefore, this is our equation x of n minus 2, which is limited between the values of n. Our old n was 0 to 2 as defined by this equation.